Hello everyone, I'm Yifeng Cao and I will be presenting our work titled ITrackU, Track a Pen-like Instrument via UWB-IMU Fusion. Demand for online education has been surging since last year and is predicted to keep increasing in the future. According to global market insights, the online learning market is expected to exceed $375 billion by 2026. Writing by hand is an effective way of teaching. To share handwriting in an online class, a teacher may use a digitized stylus on a tablet and share the screen with the students in real time. However, the limited size of tablets makes it hard to write everything on one page. Flipping digital pages causes distraction and decreases learning experience. A straightforward solution is recording a whiteboard with a camera and transmit video frames in real time. However, this requires significant network bandwidth. Large digital whiteboards exist as well, but they are very expensive. The question we asked is, can we track just the movement of the pen's tip without modifying the surface or the pen's tip? A straightforward idea could be trilaterate the movements of the pen tip. By placing multiple wireless transceivers in the environment, we can measure their distance from the pen, which can give us the pen's position using trilateration. However, each wireless range environment will inherently have a small error, which is typically at least a few centimeters. Performing trilateration with such ranging error will incur significant dilution of precision, resulting in an area of confusion too large to track a pen effectively. This need and the associated problems have been seen by others in the past, and three groups of approaches have been proposed. IMU-based tracking collects IMU data with 9 degrees of freedom to track the movement of the pen. However, due to the drifting nature of IMU-based solution, it is very difficult to maintain high precision over a long time period. Acoustic-based tracking takes advantage of the short wavelength and slow speed of audio signals. However, acoustic signals generate noise in audible frequency range, even with ultrasound signal because of hardware nonlinearities. Imagine how close the pen is to the instructor's ears. This decreases user experience. Another approach is using radio frequency signals for ranging. While RF signals suffer from environmental interference and multipass, RF-based solution can provide the required millimeter-level precision and will not be intrusive like acoustics. Yet, existing RF solutions are unable to balance the precision, range, and cost well. Our goal is tracking a pen-like instrument with RF sensing to achieve high precision, long range, low cost, and provide non-intrusive user experience without modifying either the surface or the pen's tip. We present ITrackU, a UWB-IMU fusion-based high-precision tracking solution. We make two key contributions in this work. Firstly, we propose a fine-grained UWB tracking algorithm which can track the pen tip accurately. UWB works at 4 GHz center frequency and has a high bandwidth of 1 GHz, which is very helpful to handle multipass and improve tracking precision. We affix a UWB transmitter to the pen's base, and when the user writes, the transmitter sends UWB packets which are received and processed by a 3-antenna receiver next to the whiteboard. This receiver processes the signal and produces a stream of highly accurate coordinates following the movements of the pen. Our second contribution is a multimodal fusion to enhance the reliability of the system. The pen attachment is composed of 3 sensors: a UWB transmitter, an IMU sensor, and a pressure sensor. The UWB transmitter is used for preliminary tracking as we mentioned before. However, just using the UWB is not sufficient. In cases where UWB signal is weak or blocked, IMU helps for short bursts of time to keep tracking. IMU also helps in determining the pen tilt and orientation. Finally, we propose pressure sensor-based touch detection without modifying the surface or the pen tip. All of these sensors are low-cost, lightweight, and do not emit any sound. I will firstly describe the UWB tracking algorithm to track the pen-like instrument. For ease of illustration and understanding, let's just use two antennas as the receiver. The UWB signal transmitted from the pen propagates in all directions and arrives at antenna 1 and 2 with a certain time delay. Their air-pass differential imposes a constraint on the pen's location. The receiver obtains a time domain delay profile of the received signal. This delayed profile is called the channel impulse response or CIR. The impulse in CIR graph corresponds to time of the received signal at each antenna. Note that the antennas are separated using an RF cable which helps separate these impulses in time in addition to the air-pass differential. Since the antennas are connected to a single receiver, the received signals are automatically synchronized. Therefore, when the pen is moving, the only thing which will change this time delay is the air-pass differential. So, it seems promising to use this time delay, also known as TDOA, to track the movement of the pen. However, TDOA measurements have a low precision. This figure shows CDF of the TDOA when the pen is stationary. The precision is approximately 0.1 nanoseconds, or about 3 centimeters, which falls short of what we want to achieve in tracking the pen. Fortunately, in addition to the TDOA, we can also obtain the phase of the signal from the CIR. The phase provides significantly higher precision than TDOA, less than 100th of a nanosecond. Thus, we can track the changes in phase called PDOA. So far, we have formed a UWB processing pipeline to translate PDOA measurements into the pen's movements. By tracking the PDOA change, we can get hyperbolic constraint derived from these two antenna PDOA. Now, with the third antenna, under the right geometric constraints, we can track the movement of the pen tip in 2D without ambiguity. Like most wireless technology, ITrackU is also affected by Multipass. For example, in this figure, the red pass signal is reflected by a wall and arrives at the first antenna as a delayed signal. It will affect the determination of the second pulse. ITrackU solves this problem by increasing the RF cable delay using longer physical cable lengths between antennas so that multipass dies down. We also use RF attenuators and amplifiers to fine-tune the power of each impulse to avoid attenuation incurred by long cables. More details around multipass are described in the paper. So far, ITrackU has relied only on UWB for tracking the pen, but can a UWB-only system handle everything? There are two practical problems that need to be solved: phase wrapping and low-quality CIR. What causes phase wrapping? Recall that we track by measuring the PDOA change between successive UWB packets. However, if the phase changes by more than pi between these two packets, ITrackU will have a phase wrapping error. This typically happens when the user writes fast. In this figure, we can see that when phase wrapping occurs, ITrackU experiences a significant error, and what's worse, this error will be propagated to future tracking. The second problem is low-quality CIR. This comes from the inherent instability of the wireless transmission. For example, in this figure, the first impulse is drawn in the noise because of some unexpected blocking event. This way, we cannot reliably detect all the received impulses causing errors, which can also propagate to the future. In one sentence, a UWB-only system cannot handle phase wrapping and low-quality CIR. An orthogonal stream of data are required to correct error in these spaces. That is where we turn to an ideal IMU, which includes a accelerometer, a gyroscope, and a magnetometer. We choose IMU because IMU is a good complementary sensor to UWB in many aspects. While UWB relies on wireless transmission and reception, IMU is completely self-contained. It is not affected by RF noise and has a higher sampling rate than the UWB frame rate. However, the main problem of IMU is its drifty nature. The most common way to use IMU in tracking is data reckoning, which double integrates acceleration. Small errors add up quickly in this method. So, we can use IMU only for very short interval at a time. Typically, we hope to keep the time window to smaller than 1 second. Within this 1 second constraint, IMU will be able to monitor the short-time UWB tracking results and help to correct the errors when needed. Here is the IMU processing pipeline. The initial 9DOF data will help in the rotation calculation module. In this module, we perform reference frame alignment and Kalman filtering in sequence. One of the outputs of the Kalman filter is tilt angle, which is used in calibrating the tracking bias caused by pen tilt. Another output is the rotation matrix, which is fed to the motion calculation module. In this module, we estimate the linear motion data through data reckoning. To avoid error propagation, we reset motion tracking using the previous high-confidence UWB tracking results. The output of data reckoning helps to correct errors introduced by weak CLR in UWB tracking. Similarly, we also use the output of data reckoning to compute an estimated wrapping, which compensates for UWB's phase wrapping error. The last leg is detecting when the pen touches the whiteboard. ITrackU uses a pressure sensor attached on the side of the pen to sense this. The key observation is when the pen touches the surface, a larger force is required to hold the pen firmly than when not touching the surface. The figure on the right clearly shows how sensitive a pressure sensor is to the holding pressure. During the orange times, the user is not writing anything. Once the user starts to write, we can observe a significant increase in the pressure since the user has to overcome the friction between the surface and the pen. Here's our prototype of ITrackU system for evaluation. We attach the sensors to a commodity marker pen. The sensors are connected to Adafruit M0 microcontroller. The receiver is DecaWave Track 1000. 3 antennas are placed at 3 corners of the 2.5 meter by 2 meter region. We test the scenario where IMU corrects the error of UWB tracking. In this experiment, we write on a touchscreen with different speeds. We firstly use a UWB-only solution. We observe that when the speed approaches 2.4 meters per second, a UWB-only system has a surging error because the phase wraps. However, if we fuse UWB and IMU, this error can be eliminated. Then, we evaluate the performance of pressure-based touch detection. We use marker pen, pencil, and ink pen evaluation, and we draw 5 different shapes or characters. We observe a touch detection accuracy over 90% for all shapes except dash line. For dash line, ITrackU performance is lower than other shapes because when the gap time between 2 surface touching events are too short, the pressure on the pen is not released. We finally show the tracking precision of ITrackU. We visually show the performance in the left figure in which we overlay the estimated position on the ground truth, which is obtained by camera. The maximum error in this case is 15 millimeters. We also plot the CDF of error in the right figure. As we can observe, the median error of ITrackU is 2.9 millimeters. Our paper evaluates more aspects of ITrackU, including low bandwidth consumption, comparison with commercial products, signal blocking, and etc. Please refer to our paper if you are interested. Here is a quick demo of our ITrackU tracking. In conclusion, we have shown how a pen-like instrument can be tracked at a millimeter-level precision through UWB-IMU and pressure sensor fusion because the sensors provide complementary capabilities. Our generic UWB shell for use with Adafruit Feather M0 boards is available now. We believe such technology can have a huge impact on online education and other fine-grained tracking problems. Thank you, and I am open for any questions.